Yep, so the first question is about the GPS test we did today. The range for that was approximately 7 kilometers across Botany Bay over the water. That was with a fixed distance, but we moved the antenna around on the receiving end to vary the orientation of reception. We were using a Yagi antenna for the Telemega and just basic monopole antennas for the egg timer tracker, egg find tracker. So the Yagi motion, of course, that alters the gain quite a lot. But for the monopole antenna, you basically just point it straight up and that gain is uniform in all directions. So that's how that was conducted. And yeah, the test we found in the end that we could get a connection over that distance, although we did observe a lot of interference from reflection off the water. The water, of course, will cause lots of disturbance for those EM waves propagating. So we felt the test did prove we could connect over that range, but it wasn't the most valid of tests. Moving forward, we wanted to get balloons and do altitude tests where we're getting a clear line of sight through the air to our transmitter, and that would be an even better way of testing the range. Thanks. Yeah, we've used Yagi in the past before. So the Telemega manufacturer recommends a 3-element Yagi antenna. So we just went with that for our first project. We had good results during flight. We flew to 10,000 feet, had strong signal all the way through. And speaking to our mentor as well, who was an RF engineer also, he said that the Yagi was, in his opinion as well, a good choice for our sort of operations. And of course, having 3 elements versus more elements means that the angle isn't too restricted. So if we're going to 30,000 feet with a 5 or 7 element Yagi, pointing becomes a big issue. But with 3 elements, the beam width is still wide enough that if there is some pointing error, we still get good gain on the ground. Yeah, it's an interesting one. We're going off empirical data. So our mentor, who's an L3 certified rocketeer, he's flown the Telemega on, correct me, Mitch, I think his 2-stage flight was to around 60,000 feet he was aiming for. And that system was predicted to perform well up to that altitude. He got good tracking as well for most of that flight. So it's interesting, the GPS stuff. So it's essentially based on empirical data and altitudes. We haven't had access yet to actual balloons to test our telemetry to these altitudes. So we're going off a lot of what we know from people who've worked with these systems in the past. So the fact that the Telemega is being so thoroughly flight proven on high altitude flights using Yagi antennas, we're confident that will work for our rocket as well.
All right, now to completely change gears, and I'm going to start talking about aerostructure stuff because that's my area of interest. So, so you mentioned in your technical report that you're using fiberglass for your nose cone for RF transparency. What made you go with carbon fiber? So I know you went with that for the nose cone, but what made you go with the carbon fiber for your other airframe segments? What was the decision-making process there?
I think we'll hand over to Cam or Mitch for this one.
Yeah, so we chose to use carbon fiber as we can go with 4 layers of carbon fiber, which is for our strength, and we've done shear tests in the past to prove that's strong enough for what we're looking for, and it's just a lighter option compared to fiberglass.
Carbon fiber just has a much higher strength to weight ratio, so we can actually get some really, really thin tubes, but still not experience any buckling throughout our flight. So we probably over half the weight of the tubes by choosing carbon fiber over fiberglass.
Okay, that makes sense.
Yeah, it's only 4 layers of
Yeah.
carbon fiber compared to
As opposed to, yeah.
fiberglass, which are like 8 to 10 layers.
Yeah. And then for you, I see for a lot of your bulkheads and the tip of your nose cone, you went with 70-75 aluminum, which is a bit of an unusual choice. Most teams are using 60-61, where they use aluminum. So what went into the choice to use 70-75 over 60-61?
Yes, I think that's two points there. So we got an aluminium sponsor, which was able to provide both 7075 and 6061. And 7075 has a higher strength to weight ratio than 6061. So if we're not designing a piece for volume, if we're designing it purely for strength, we can actually reduce the weight for that, even though it's a small amount. Since it was being supplied, we're able to do
that. Lucky you guys.
Yes, it's quite nice.
Yeah. Okay, and then I guess my next question is, so you've got these retractable rail buttons on your rocket. Can you speak to I guess two questions are, so first off, because these are spring loaded, do you experience additional drag on the rail because everything is being pulled against the rail? And then have you done any testing on that? And then secondly, what does the drag decrease? How much less drag do you get by having these retractable rail buttons as opposed to ones that stay out? Or I guess as opposed to what are the advantages of this versus going to a tower launcher system?
So just for the first one, the extra drag on the rail, from all our tests on the ground, it's only about a Newton that the actual springs are pulling the retractable rail buttons back in it. So there's very minimal change to the drag on the rail. It's just enough to pull the rail button in and won't impart any moments or anything like that onto the rocket. It should gain us about 1,000 to 1,500 feet from compared to having rail buttons that stick out with an aerodynamic profile. And the reason it's more of an intermediate step for us before we would do something like a tower. Currently, we only have our own launch rail. So while not being able to have a tower, we've chosen to use this.
Okay, that makes sense. Oh, and Matt has a question, another electronics question, and I guess I'm interested in that as well. What's the pad stay time for your electronics? And then can you also talk about power systems more generally?
I'll hand back to Matt for that.
Yeah. Yep, sure. I'm just checking. I don't know if the number made into our report in the end, but we did do some testing on the current draw of our flight computers, which is in a larger report the team made as a detailed design report. And the results from that, I believe, I haven't got it right in front of me here, but it was going to be a few hours for each of those computers. So we reasoned that would be sufficient time for idle on the pad, and then for the flight to take place, and then to give us a buffer as well for recovery. If something does go wrong, ample time to track down the rocket. In terms of the batteries we're using, we've chosen to use LiPo batteries for all of our flight computers because they do provide a high energy density. And in particular, some flight computers like the Telemega, for example, particularly require a 1S LiPo battery. They don't run on like 9-volt Duracell batteries, which are often used for model rockets. So in order to standardize things and have high energy density, we chose LiPo batteries for all of our systems.
Okay. Do you guys do anything in terms of yeah, so Matt has the
I can answer that now, but
yeah.
if you were
Go ahead.
halfway
Yeah.
through asking a question.
Yeah.
So it's made of just a normal 15 by 15 rail button. It's just been sanded down so that we're able to attach it into our mechanism. So there's not too much concern with the strength of the rail button, as this is already being used on standard 15 by 15 rail buttons.
And then I guess going back to the deployment side, so I noticed for your calculations for your CO2 deployment, you assumed that it's isentropic expansion. Can someone speak to what the justification was for assuming that the process would be isentropic and reversible for that assumption there?
I believe that the CO2 calculations were just done to get an initial guess on the size of the CO2 canisters needed, and then we will be doing deployment testing to verify. So currently we've got 38 gram and 45 gram canisters in the lab, and we'll be deployment testing when we can to verify that the CO2 is enough for deployment.
Okay. As a physicist, I think I think the use of an isentropic reversible process there for your estimation, I have a feeling that will be off pretty significantly, and you might want to look into redoing those calculations with an adiabatic Joule expansion, because effectively, if that seems like it will be more applicable for that sort of a scenario where you basically are dealing with free expansion of a gas.
Yes.
Yeah. And then I may have missed this, but what do you guys use for your switches, for your avionics? What types of switches?
Yep.
Yeah. So in our AV bay we use 12 Omron SD single pole double throw switches, and we align them all in different phases. So we have main power for each flight computer completely separate on a separate remove before flight pin, and on top of that we also have a separate remove before flight pin for all of the energetics of both drogue and main deployment events. That's just to separate out. We can cycle the flight computers on and off to ensure that they're working whilst they're inside the coupler, but without enabling the energetics to have the possibility of going off until the very last second of preparing the rocket on the pad. Okay.
So those are the Omron like push button switches, and you're just using a remove before flight pin to like trigger and depress them. Is that correct?
Yeah. So yeah, they're the lever action ones.
Yeah.
Yep. And we've got a 3D printed switch plate that holds them together with a M3 hole that the lever actions like come out into, and then we have a M3 remove before flight pin that will push and depress that lever, causing an action.
Okay.
And that also allows it to be side on from vertical, which means that we don't have to worry about any sort of flight forces ever having any chance of triggering that switch.
What about vibrations? Have you done vibration testing to make sure that any flight vibrations wouldn't momentarily flip one of those switches, or do you know how your electronics would respond to momentary power loss from one of those switches inadvertently getting jostled momentarily into an off state.
Yeah, we haven't completed at this time full vibration testing. We have ensured that there is good clearance between the print so that nothing actually interferes with the lever action itself. We've also ensured that there have been tests of power loss on our systems. So, for example, we know that some of our flight computers have capacitors that can handle momentary power loss. However, we have to run further tests on how this may affect our system if it was for longer than just a moment, and how our system may be able to recover. That's something that we're planning to do with a further range testing at the same time.
Sounds
Just
good.
to add to
And
that as well, our previous competition rocket, Silvereye, utilized the same style of switch, as well as our L3 mentor, Stuart, he uses the same sort of switch on his rocket. And some of my high power rockets as well, they've used also those lever arm switches. So based on all those different flights, we're confident that this switch design will be adequate under flight loads.
that sounds good. And then, yeah, the question from Matt, the biggest challenge you had with the project and how you mitigated that.
Mm-hmm. Gosh, where to start? I think the one that jumps out to me is probably collaboration in an online environment. So when we build our rockets, we like to get together in person around a whiteboard, draw lots of stuff, talk to each other. And when we had to go into lockdown, it was a big shift to go from working that collaborative way in person to working online. The challenge was to maintain that sense of being together without being physically in the same space. So what we did was we got into Microsoft Teams and we just tried getting our Teams environment set up in a very good way that enhanced this collaboration. So we've used lots of notebooks, for example, to organize our meeting minutes and notes for collaboration. We've got an extensive SharePoint database for all of our files. We use lots of Zoom meetings so we can talk to each other and get some face-to-face interaction as well. And then by doing all these things, we managed to, even though it's not quite the same, still collaborate throughout COVID and continue our design process. So I think
Okay.
that's
Yeah.
that.
Yeah, I think we can probably call your guys' Q&A here, unless you have any other questions, so that you guys can get some sleep.
Thanks, and thank you, Matthew. We hope to be there next year in person.
Yeah. Oh, yeah. All right. Thank you, guys.
Okay.